Hi, Chemistry 11. So I'm going to start today by reviewing some of the electron configuration problems that I didn't review in the last lesson. And then I'm going to get on to bonding the whiteboard part of the lesson, and also have the screen lesson for bonding. This is lessons 3 and 4 combined from your notes. So I'm going to try to go as quick as possible. Questions 1, 8, 16, and 17 are the ones I want to review from yesterday. So question 1, they're asking for the full electron configuration of sodium. Remember, when you're making an electron configuration, you want to start from the ground up, the ground floor up. Ground floor is your 1s orbital, and 1s subshell as well, with one orbital, has space for 2 electrons. Once it's full, and you know it's full if it's 1s2, just for the 2 electrons, then you have to start adding electrons further up. Your next orbital to work with is the 2s orbital. It'll be full once it's got 2 electrons in it, because that's the way it is with all s orbitals. Those are remember your S block, alkali metals and alkaline earth metals, and helium for that matter, S block. Once you go up from that, then the next kind of orbital you're going to fill right after an S is a p orbital, at least for periods 2 and 3. So for periods, well, I guess sodium is in period 3, but you're building up from the second period. 1s2, 2s2, 2p6, and 3s1. Notice that adds up to 11. 11 protons must balance with 11 electrons. By the way, if you were doing the full electron configuration for the ion, you'd be dropping off that last 3s. You'd be dropping off the 3s1. Germanium, we're just starting like we did before, and then building onto that, right? Because you build from the ground up. You add electrons from the ground up. So for germanium, it's a lot longer. We have to have a d block orbital in there. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p2. So really you're reading this from left to right and down, just like you would read a book, in terms of the order in which you're adding the electrons. You do find, though, for transition metals, there are some weird little exceptions where a more stable configuration for the D block elements is often to fill D shells up to the half full or pairs or full, and kind of steal away from some of your 5s electrons that you already added to. So for niobium, for example, core configuration, we end up with the krypton core. 5s2, 4d3 is what you might expect, whereas in reality, an electron gets stolen from the 5s orbital, and you end up with 5s1. It's going on to the 4d orbital, so you end up with krypton 5s1, 4d4. And for sulfur, by the way, your core is neon, and then your valence shell electrons are going to be 3s2, 3p4. Pretty straightforward stuff. Lessons 3 and 4, there's a number of questions I want to review. That's why I'm kind of going quickly. For oxygen, I asked for an electron configuration. Remember, this always starts with the element symbol, in this case O. And then I say, hey, what are the valence electrons? What are those outer shell electrons? Well, the outer shell is shell number 2 with the 2 subshells, 2s and 2p. Subshell 2s has space for 2 electrons, 2p has space for 6, but we only need to put electrons in 4 of them. So what it ends up with is 1s2, 2s2, 2p4, and I put a little circle, or a circle around the 2s and the 2p subshells, right? In other words, shell number 2 is being circled. And they're all like that, so I'm only going to review one. For question 2, what you're being asked is to predict ionic, covalent, or metal-metal. In practice for Chem 11, you don't have to worry about metal-metal in any detail beyond your knowing that, yeah, it can exist. Metals can bond covalently, but let's not worry about that past here. I hope you're at a point where you can look at the periodic table and identify where are the metals, where are the nonmetals. Your nonmetals are towards the right of the periodic table. Your metals are towards the left, and between you have the semiconductors, also called semimetals or metalloids. Here, nitrogen being a nonmetal, oxygen being a nonmetal, the bonding will be covalent. When you're bonding a nonmetal with a metal, the bonding is ionic. Pretty straightforward stuff. But there's subtlety to it when you're starting to bring in this whole concept of electronegativity. It's not necessarily an either-or proposition. Electronegativity is the ability the tendency for an atom to pull electrons towards itself, to the exclusion of some other atom. So for example, fluorine is the most electronegative of all the elements, with an electronegativity of 4.0. Cesium, at the opposite end of the periodic table, the opposite corner, has an electronegativity of just 0.7. It has a strong tendency to donate its electrons, whereas fluorine won't donate its electrons to anything. It's got the highest of all electronegativities. So there we see from the periodic table, and of course we're ignoring the noble gases, helium, neon, and argon, because they don't engage in any chemical bonding. And let's not worry about the other noble gases anyways. The closer you are to fluorine, the more electronegative you are. So if you look around fluorine, we've got oxygen, sulfur, and chlorine. Oxygen and chlorine are the closest to it. Of the two of them, oxygen is more electronegative. Counterintuitive, you might have thought it would be chlorine, which reacts so powerfully, but oxygen is actually a powerfully reactive gas and very electronegative. So if we look at how that plays out with the kinds of bonds, you're given three different options here. One is an ionic bond. Two is a polar covalent bond, where the electrons are being shared, but they're being shared unevenly. And then nonpolar covalent means effectively even sharing of electrons. This becomes important when we're starting to talk about physical properties. Water, H2O, hydrogen, oxygen, hydrogen. The oxygen is far more electronegative. In fact, the difference, 3.5 to 2.1, is 1.4. That's nearly, by this definition, an ionic bond. Now, of course, we know that water is not an ionic compound, but does have a polar covalent bond. In practice, what this means is that oxygen is pulling electrons away from that hydrogen. As a result, the hydrogen gets to be a little bit positive, because after all, having a negative taken away from you makes you positive, and the oxygen end of it ends up being a little bit negative. The old penny trick, where you see how many drops of water can you put on a penny, comes down to this. A lot of people are surprised by the fact that the water balls up, and I've seen as many as 32 drops of water fit onto a single penny, because the water is stacking up. What this comes down to is what's called hydrogen bonding, where those electronegative ends of the molecule, the oxygen in other words, are kind of gripping on at a distance to the positive ends of the water molecule, the hydrogens. Those temporary bonds are called hydrogen bonds, and they're a result of the polar covalent nature of the hydrogen-oxygen bonds within the molecule. So as a result of this, we can see what I'm reviewing right now, by the way, is this right here. So for the case of a sulfur-hydrogen bond, SH, sulfur has an electronegativity of 2.5. Hydrogen's is 2.1. The difference is 0.4, and this puts it just on the edge between polar covalent and nonpolar covalent. By the way, this is a real bond. This actually is found in chemicals. Here's a 3D rendition of a chemical, methane thiol, that has an SH bond. What this actually means there, those weird triangles and little dotted lines, it's a statement about the three-dimensional arrangement of the hydrogen atoms around that carbon atom. They form a little tripod. Imagine that my fist here, my hand here, is the carbon atom. The hydrogen atoms are repelled from each other as much as they can be, facing away as much as they can be because they're repelled. And so that's what I'm trying to show using that notation, which you'll see when you look up molecular diagrams, for example, on Wikipedia, looking at molecular structure. They use these dotted lines and little triangles to show. What I'm getting at here is called Vesper theory, by the way. Valence shell electron pair repulsion, which I'd like to get into a little bit later, maybe with some kind of extra information lesson for those of you who are interested. It's not dealt with a whole lot, I don't think, in the textbook, and I'd like to explore it more. So that is an example of question 3. You saw them all the same way. You are using this table of electronegativities, which you can also get from the website Dynamic Periodic Table, those values, and then finding the difference assessing, is the bond ionic, non-polar covalent, or is it non-polar covalent where the electrons are shared basically equally? An example of a non-polar covalent bond would be like CH bonds are non-polar covalent. Carbon, yeah. In fact, well, let's look at, say, I don't know. Yeah, CH bonds are good enough. 2.0 to 2.1. Yeah, 2.5 to 2.1. Well, it's a difference of 0.4. I guess that's almost verging on the edge again of polar covalent. Anyways, when there's a low difference, the electrons are being shared equally, and that's what you need to know, and it makes it a non-polar bond. The last thing to look at is stating possible formulas for compounds. You use for this the table that is given on question 4, also given in your notes. Here's the table for question 4, right there. Valence shell electrons are the electrons in the outer shell. What's called the valence of an electron is a statement really of how many chemical bonds it is capable of forming. So the pattern for valence shell electrons is 1, 2, 3, 4, 5, 6, 7. We're starting with group 1 like sodium, group 2, beryllium, and so forth, working all the way up to the halogens at 7, and then you drop down to 0 because valence shells are considered reactable electrons. Noble gases don't get involved in chemical reactions, so a 0 is assigned to them. The valence is a prediction of actually how many chemical bonds that you're going to see being formed for them to satisfy the stable octet rule, which is what you want for periods 2 and 3. 8 electrons is a stable outer shell. So what does that look like, or how can that be shown? It can be shown with what are called Lewis structures. I'm going to do a Lewis structure for fluorine and a Lewis structure for phosphorus, P and F. For Lewis structures, you want to imagine some kind of square around your element symbol, right? That's what I mean. I won't leave it there, but place an imaginary square, have an imaginary square around each element symbol. I am now going to add the valence electrons to display them on the phosphorus atom. And I add them like this. Add one at the top. You can start anywhere. Now on the side, now on the bottom, now here, and I'm stopping at 5. There are 5 valence shell electrons for phosphorus. Notice I've got 3 spaces where there's only 1 electron, low in electrons. In order to satisfy the octet rule, phosphorus is going to need to fill that with electrons to get its required 8. It's going to be, in other words, able to form 3 single bonds to satisfy that rule. How about fluorine? Fluorine is a halogen. As a result, it's going to need 7. 1, 2, 3, 4, 5, 6, 7. Only 1 unpaired electron. Now, I'm saying possible compounds because there's all kinds of possible compounds that you can form from phosphorus and fluorine. This is just one possible compound and how to find it. The valence for phosphorus, 1. The valence for fluorine is 3. For this very simple solution, we just say, all right, I got that wrong. The valence for phosphorus is 3, the valence for fluorine is 1. For this very simple solution, we just switch our valences. The 3 goes over here as the subscript, the 1 goes here as the subscript. What we end up with is P1F3. Now, of course, you know from when you started chemistry that you never use subscripts of 1. So PF3 is the compound. In other words, phosphorus trifluoride. What does that look like? How can we display that? How can we represent the molecule? I'm going to draw fluorines in red and phosphorus in blue. In other words, take my fluorine and put them over here on the phosphorus. Here's a fluorine down here, satisfying this electrons needing to be paired, needing to be part of a pair. Here's a fluorine here. And here's one right here. Look at this. Fluorine has satisfied the octet rule by gaining an electron here, here, here. 3 different fluorine atoms have satisfied the octet rule. Phosphorus has also satisfied the octet rule by getting 1 each fluorine for each electron from each of these fluorines. So this is an electron dot diagram for phosphorus trifluoride. Now, in practice, you're not going to normally see them displayed this way because it's a lot of dots and it's pretty clumsy. What you can do instead is you can show the dots that are parts of chemical bonds as lines. I'm just going to do this as a blue line. There, there, and there. That's a little bit cleaner. That's a way you'll often see it displayed. Sometimes they won't even display. Sometimes your diagrams won't even display the lone pairs of electrons. They'll just show the bonds. So it might be shown instead like this. There's a lot to unpack right there. First of all, I threw away those unpaired electrons. Anyone, people who've got this far in chemistry and have been taught Lewis structures are going to know that fluorine's got unpaired electrons. Here, by the way, notice that the phosphorus, we've got another tripod situation. The fluorines are not facing off in just any old directions. They're repelled from each other like that, but why are they seem to be pushing towards each other? They're doing that because there's also a lone pair of electrons right here, not bonded to anything. How do I know? There they are right there. By valence shell electron pair repulsion, they are pushing away the electrons that are bonded to the fluorines. So that's something I want to deal with maybe a little bit more in my bigger lesson on Lewis structures, but that's something I also wanted to deal with here. And I hope that helps as a way of exploring answers to lessons 3 and 4. 11. So this is your screen lesson for lessons 3 and 4, ionic bonding and covalent bonding. I'm just going to pair this up with a whiteboard lesson. So just kind of to lead into this a little bit, here's a couple diagrams for you, pictures for you. One here is of some crystals of sugar, and down here under microscope also you have some pictures of salt. Both of them transparent, both of them in a crystal form, fairly similar density. Superficially they look quite similar, but of course in personal experience you know that when you start to look at many of their other properties you find that they're really very different. Well, one thing I'd like to show you about the differences between them is that they're actually formed at a molecular level using, they have very different structures at a molecular level, and I'm going to get back to that in a little while. First of all, I want to look here at the start of lesson 3. Now, what you're seeing right here is a simple applet that shows you green balls here are large positive charges, and the small white ones are negative charges. All right, so each of these is acting as a point charge, and what you're seeing is these things, little white balls, they start out at the side, they move kind of slowly, and they start to whip towards the green ones, and either they form an elliptical path, elliptical orbit, like that one right there I'm just following, which is kind of like a longer oval, or they crash right into the positively charged ball. What you're seeing there is how can I put it? An animation of electrostatic attraction, where the closer the negatively charged object is to the positively charged object, the greater the force, and as a result, you're seeing the greater is the velocity of the object. As it gets closer, it goes faster. Gravity acts in the same way. Now, you might have thought going into this course that electrons orbiting the nucleus are a little bit like that, little tiny negative charges orbiting around a positively charged nucleus. But the problem with that is, well, you look what's happening right here. These electrons are, if we think of them as electrons, are hurtling towards the positive nucleus, but they're doing something that electrons shouldn't do. Really, they're striking these positively charged balls and then annihilating themselves. So, in other words, and if this happened in matter in nature, then matter could not exist. Instead, we know from the last lesson that electrons relative to protons don't behave exactly like that. Specifically, the thing about electrons is that relative to a nucleus, they're only able to occupy certain positions. Those positions we call orbitals. And if we looked at how orbitals are arranged in different shells and subshells in the last lesson, so I'd refer you to that last lesson where we looked at that. I was giving you shell numbers, where here they're shown as values n. Those are called quantum numbers. So we go from n equals 1, 2, 3, and 4, and so on. These are electron shells that can exist around an atom. Electrons can't exist in any shell, say 1.5. There's no such thing. They can't exist in here. They have a 0% chance of probability of being found at certain locations and a much higher probability of location of being found at certain other locations. So that's the nature of how electrons occupy space around the nucleus of an atom. We looked at how also it's possible for electrons to drop from higher energy levels down to unoccupied lower energy levels. No two electrons can occupy the same space. That's called the Pauli exclusion principle, but they can be close to each other and they can occupy an orbital in pairs. When they drop from a higher energy level, like right here, down to a lower energy level, say from 5 to 3, they emit a flash of energy equal to the amount of energy that has been lost in this relative to this. These being further apart from the nucleus, they have energy and a kind of potential energy that they will release when they fall back towards it into an empty or unoccupied electron space. That energy is emitted as a particle of light called a photon. Now, it might not be a visible particle of light. It could be an ultraviolet photon, which you can't see, which is high energy, or it could be infrared, which you also can't see, which is low energy, makes you feel warm, or it could be visible light, and this forms what's called an emission spectrum that is emitted by an excited sample of a particular element or any shape of matter. Now, what we looked at as well the other day is we looked at electron shells. We looked specifically at how the periodic table is arranged. I'm going to look at that again in a couple of ways today. And here I'll just remind you that this is arranged in blocks. The pink here is called an S block. The outer electrons are in what's called an S subshell. So remember, the rows are periods here, columns are families, but right now we're interested in the periods. So here, everything for all these elements here, they all have their outer electrons as being in the S subshell. These guys down here, once you get to period 3, this is once you get to period 4, you've got shell 3 electrons here in the 3D shell. Remember, this shifts down, and this is your 3D shell right here, and there's D shells for periods 3, 4, 5, and 6, as we see right here. These are the D block elements right here. Tin has D shell electrons. It's got all the D shell electrons that these elements here have, but its outer shell electrons are in the P block, because this is the P block of elements right here. So what we looked at is how electron shells get filled from the inside out, from the bottom floor upwards. So that here, this 1s, this electron right here around hydrogen is in the 1s subshell, which is the only subshell in shell 1. And it's 1s1. It's, as you can see over here, right there, tells you the electron configuration. There's one electron in subshell 1. Now there's 2 electrons in subshell 1 because we're dealing with helium. Filled, okay. Now we have to go to the next shell because shell 1 only has space for 2 electrons. And we saw how we're adding 1 electron at a time. We are filling the S subshell with the 2, and then the P subshell can only ever fit 6. So we looked at how electrons were added. I also showed you a little bit about the full electron shells. Now, in actual fact, what you're seeing here, the thing at the top says Lewis, but really what you're actually seeing here is a little bit more like Bohr diagrams because all the electrons are included. Although the Lewis structure, the outer electrons, the valence electrons, are shown here in red. Now, what again you're seeing here is for periods 2 and 3, we're following that octet rule where a full outer shell has got 8 electrons. What I did tell you, what you're going to see in the whiteboard lesson is I'm also going to explore the topic of valence, but just so you know right here, the valence electrons in, say, fluorine, it's got 7 valence electrons. 9 electrons in total, 7 of them are valence electrons. And then chlorine in the same group is the same way. Now, a simplified way, though, of showing this is the Lewis dot structure. For the Lewis dot structure, for making them, you take the element symbol, like Li right here, and you have an imaginary square around it. You don't have to draw the square, but just imagine a square around it. And you start adding dots. Each dot represents an electron. Normally when I'm doing them, I just go count 90 degrees at a time, go clockwise or counterclockwise. It doesn't really matter. Here the format they're using is Li and then Be. They're putting them across from each other, and then B for boron. Notice that we're only ever occupying one side of the square, and by the time we get to neon, that imaginary square has got 8 dots around it, 1 for each electron that is being progressively added to the shell in period 2. Look at this. This is NS2, NP6. Well, I should say 2S2, 2P6. That's the outer shell structure for neon. The full configuration is 1s2, 2s2, 2p6. In the same way that for, say, argon, it's 1s2, 2s2, 2p6, 3s2, 3p6 is how you get to argon. That's what all this gobbledygook means up here. So those are Lewis symbols, and we're going to get more into Lewis symbols later, in terms of how they're used to actually display the structure of an atom. Something I want to explore here is this concept, though, of electron shells. So what we're seeing for each of these rows here, it's a period, yes. What we're doing here as we go from lithium up to neon is we're progressively filling that shell for period 2. All of these electrons, lithium through fluorine, all those atoms, they have open shells because their outer shell is not full. Only for neon do we have a closed shell. That outer shell is a full shell. It can't have any more electrons in it. The non-reactivity of neon comes down to it having that full outer shell. So that's what I'd like you to know about that part of your notes. But moving along, but staying on this figure right here, I'd like you to notice something. Here for lithium, we've got 1 electron only, and that electron is a lone electron. For beryllium, we've got 2 of them. Notice, when we added more electrons, we didn't put them next to each other. We add 1, and then we find another side of the box, and we add another to that. By the time we get to carbon, we're still doing that, but look at nitrogen. A dot has been added, then you move 90 degrees, add a dot. Move 90 degrees, add a dot. Move 90 degrees, add a dot, and then repeat again. Now, one of these electrons, one of these sides of the square is full of electrons. They are paired. This is an electron pair. These 3 here, however, are lone electrons. So this is an electron pair. The others are lone electrons. These electrons here can become involved in chemical bonding because, in other words, after all, to satisfy the octet rule, an electron has to be bonded here, paired with this one. One has to be paired with this one right here, and one paired with this one right here. Once that's the case, nitrogen will have satisfied the octet rule, and it can do that by chemically bonding with other substances. So the number of lone electrons is called the valence of the atom. Not to be confused with valence electrons. Valence electrons are the outer shell electrons. The valence of an atom is the number of unpaired electrons within the valence shell. So the pattern works like this for periods 2 and 3. 1 valence, 2 valence, 3 valence, boron, 4 valence for carbon. Now we go down, 3, 2, 1, and neon has 0 valence electrons. No electrons that can become involved in chemical reactions. So there's a distinction there to make, an important one, because what this does is it actually allows us to predict how many chemical bonds can be formed when structure forms a covalent, an atom forms a covalent bond. The number of bonds that will be formed, it's a simple prediction. It's going to equal the valence. Nitrogen can form 3 bonds. This electron here becoming involved in a pair, this one here, and this one here. These 3, when they are paired with other electrons, will form full orbitals, and that corresponds to 1, 2, 3 bonds. Just like with oxygen, it's 1, 2 bonds, and fluorine just needs 1. And this is a general pattern by column. Everything in this column will gain a stable octet with just 1 bond. All elements in this column gain a stable octet by forming 2 bonds. Going to carbon and silicon, well, they need 4, but then we go back down to these. It's a little bit, I'm not really sure, I don't really like to talk about forming bonds when we're talking about these metals right here because they are ionic, but their valence, like for aluminum, for example, is equal to the ion charge. Notice this. Notice this. These outer electrons, these valence electrons of aluminum, correspond directly to the ion charge of aluminum. Aluminum gives up these 3 electrons, in that way has a stable octet because it's going to have the outer electron structure of neon, and also gains in the process a positive 3 charge. So the ion charges kind of work parallel to the valence. Your ion charges are +1, +2, +3. There's no such thing as a +4 ion charge. Well, not for these guys. They don't form that, so no charge. But now, -3, -2, -1, and again, no stable ions are formed for noble gases. So the valence of an atom and the ion charge of an atom directly correspond to each other. So we'll get back now to sugar and to salt just briefly. I'm going to show you exactly how they're different. They're different because they're made of different chemical elements, but also because they have different kinds of bonds. In the case of salt, what we're doing is we're forming an ionic bond. The sodium gives up its 1 valence electron. Remember, this would have 1 dot next to it. It gives that one up. That 1 electron becomes involved in chemical reactions. It's donated. The chlorine becomes chloride when it receives the valence electron from sodium, and it gets a negative charge. There is electrostatic attraction. Remember electrostatic forces? There's an electrostatic attraction between the ions. But here's one catch. Where is it? Right here. This gives you a little bit more background about sodium chloride. Here's one little catch right here. What we have right there, 0.236 nm, that means 0.236 nanometers. Okay? What that means is that's at the lowest energy point between a sodium ion and a chloride ion. When a sodium ion and a chloride ion are attracted to each other, they will only get so close. They will click together and they can't get any closer. If you try to push them closer, they actually will be repelled from each other. And the system as a whole gains energy because it wants to be pushed away. Similarly, if they're, say, this far apart from each other, they will click together until they're at this lowest energy level. So there is a very clear and distinct ordering in that structure, and it's that constant distance, in this case of 0.236 nanometers, that governs the crystal structure of sodium chloride. It's not like that for, where is it? It's not like that for sugar. In the case of sugar, we're forming what are called covalent bonds. The covalent bonds are different in that electrons are shared. And what is the reasoning behind this? Why do we sometimes have electrons being shared and sometimes have them being donated? It comes down to what's called the electronegativity of the elements. The dynamic periodic table is an awesome website. Here, what I've done is I've clicked on the Properties tab, and I've clicked on this thing called electronegativity. Electronegativity is the tendency of an atom to attract electrons towards itself. Atoms with very low electronegativity will freely give up their electrons, like cesium, for example, the most reactive of the stable alkali metals. Fluorine is given an electronegativity of 4, meaning that it attracts electrons the most powerfully of all the elements. Not needless to say, a reaction between fluorine and cesium will be powerful indeed. So that's electronegativity. The closer you are to fluorine, the more powerful your tendency is to attract electrons. This gives you a lot of insight into how molecules get built. Whether you're going to form an ionic or a covalent bonding depends on the difference in the electronegativity between the elements that are involved. When there is a large electronegativity difference between two elements that are going to be involved in the chemical reaction, you're more likely to have electrons being transferred completely rather than shared. If, for example, oxygen forms a compound with calcium, you make calcium oxide, well, we've got a big difference there. 3.44 is the electronegativity of oxygen. Calcium is just 1. A big difference like that, specifically over 1.7, will give you an ionic compound. An extreme example in the other direction would be H2, hydrogen. In the case of hydrogen gas, two hydrogen atoms are joining together and forming a molecule of hydrogen gas. Well, the electronegativity difference between the two hydrogen atoms is 0. There is no difference between 2.2 and 2.2. Because there is no difference, the bond that is formed is covalent, and specifically it's called a covalent nonpolar bond. The electrons are being shared perfectly, evenly between the two elements. We can also examine situations where very similar elements form chemical bonds. If, for example, we have a compound that is made of nitrogen and, I don't know, let's say one that's made between chlorine and bromine, there is a fairly small electronegativity difference between them. Say chlorine bromide, it's only 0.2. They're both really electronegative. Because that's the case, the bond that will be formed will also be covalent. It would actually be called a nonpolar covalent bond because they're not all that different in how electronegative they are. So that's the concept of electronegativity, and you will see that coming up in your worksheet. The last aspect of this is for lesson 4, predicting a possible formula for a binary covalent compound. But you know what I'm going to do? I'm just going to draw your attention to the fact that there is a table below lesson 4 that gives you the relationship between the column, the valence, and the combining capacity. And what you're going to see from that is the combining capacity, that is to say, the number of bonds that an atom needs from periods 2 and 3 to form a stable structure, a stable chemical structure, is equal to the valence of that element. That's all for now. I hope you found this useful.